Okay, we're back. In the last video, I kind of left you in a little bit of a cliffhanger. We basically got to this point where we have the two conformers with the methyl group on the rightmost carbon on both conformers, the ethyl group one position to the left of the rightmost carbon on the front end of the molecule. And I pointed out that what used to be equatorial on the first conformer is now axial. What used to be axial, now it's equatorial. Um, So what we're going to do is we're going to take a look at the Newman projections to figure out what energy profiles we're dealing with in these molecules. So what you basically have to do is look at each one of the carbons that have the big R groups, right? The ethyl groups, the methyls, or whatever other group aside from hydrogen you have. And you have to look at the bonds that go from that carbon bearing the R group um, onto the opposite portions of the cyclohexane ring. So in this case, we're going to look at the carbon that bears the ethyl group, and we're going to go to the left side, and separately we'll look at the same carbon that has the ethyl group going towards the back side onto the carbon that bears the methyl group. And then at that point we'll look at the carbon that bears the methyl group, and we'll do the same type of analysis. So first things first, in relation to the carbon bearing the ethyl group, if we look at this such that the ethyl group is on the front side of the Newman projection, technically speaking, the projection or the point of view is happening through the red bond from the bottom right portion of the molecule to the top left portion, right? So this is the point of view. So in that case, the ethyl group is technically pointing towards us. The cyclohexane ring is pointing towards the inside of the screen, and the hydrogen is exactly on the screen itself. So what you see right here is that ethyl is on the left side, cyclohexane, the cyclohexane bond is on the right side, and the hydrogen is down. And if we look at the carbon here on the back end of that red bond, hydrogen is straight up. You have two things on the bottom, so you have your Y down on the back portion of the molecule. And once again, the hydrogen is to the front, the cyclohexane is going towards the back. So hydrogen is to the left in the Newman projection, and the cyclohexane is to the right. And one thing that might help you with this type of analysis is that the cyclohexane portion of the molecule, because it's a ring structure, it always has to be on the same side for both the back and the front portions of the molecule. So you'll have cyclohexane here, and you better have cyclohexane down there as well. All right, now from the point of view of the green bond, so if we still keep the ethyl group on the front, we have ethyl group going to the right. We have the red bond, which is basically a CH2 or the cyclohexane portion of the molecule on the left side of the molecule, and then we have the hydrogen pointing straight down. So we have that Y up shape on the front, ethyl on the right, cyclohexane on the left, hydrogen on the bottom. And once again, if the cyclohexane is pointing to the left on the front side of the molecule, it will also be pointing to the left on the back portion of the molecule. So looking at the back portion of this green bond, we see that the methyl group is pointing straight up, so we have it pointing straight up on the back portion. Cyclohexane is pointing to the left, and the hydrogen is pointing to the right, as depicted exactly on the Newman projection right here. Okay, so this is all from the point of view of the carbon that has the ethyl group bound to it. From the point of view of the carbon that has the methyl group bound to it, you have two possibilities. You can look at the Newman projection going from methyl bound to methyl bound to that carbon to the carbon that has the ethyl group, but we've already done that. In fact, that's the Newman projection right here. So really the only thing we need to account for is the bond of the carbon that bears the methyl to the back side of the cyclohexane ring, right? So basically this purple bond. And once again, the projection is going to be from, now in this case, the top right portion of the molecule to the bottom right portion of the molecule. And that means that the methyl group is going to be on the front portion of the Newman projection. So we have one thing on top, we have two things on the bottom. You have the Y down shape in the front side of the Newman projection. On the back side, you have two things up and one thing down. So you have the Y up. And like before, methyl is pointing up, the cyclohexane is going to the left, the hydrogen is going to the right. So we have the cyclohexane on the left side, and if cyclohexane is on the left side on the front, it better be on the left side on the back side as well. And that's exactly what we see. We have cyclohexane pointing left, hydrogen pointing right, and another hydrogen pointing down. So this is the look on the back side of the molecule. So what this ultimately gives you is all of the possible gauge interactions that you could have. And this is the reason why we're focusing on the carbons that bear the ethyls, the methyls, and any other carbon group bound to it as a substituent, because those are the ones that are going to start raising the energy of your cyclohexane. So what we basically do is we look at the interactions of the neighboring groups, and technically these are all gauche interactions, and this is the reason why the chair conformation is the one lowering energy compared to the boat or the twisted boat, because in the boat conformation in particular you're dealing with eclipse conformations, but the stagger conformation, gauche conformations, those are the ones that you encounter in the chair conformer of cyclohexane. So what we're going to basically do is we're going to look at the interactions of the neighboring groups. But to keep this simple, since everything in cyclohexane is going to have cyclohexane next to cyclohexane, we're totally going to ignore that interaction. That's basically common in all of the structures, so that's not going to change. That's going to be in all of them. So just treat it as your background normal initial energy. But then what we're going to do is say, okay, well, cyclohexane next to some other group, treat the cyclohexane portion as if it were methyl in terms of looking at the table of energies down here. Okay, so we're going to basically do that. Cyclohexane R, we'll treat it as as ethyl. Yeah, we'll treat it as ethyl interactions just to make it a little bit more robust. So not methyl, but rather ethyl. All right, so um, as I said, we're going to ignore the cyclohexane to cyclohexane interaction. Methyl to hydrogen, it's going to be treated as cyclohexane to hydrogen. Okay. So when we look at the structure here on the left side, notice that we have ethyl next to hydrogen that has an actual energy associated with it, 0.42. We have another ethyl on hydrogen that's 0.42, but hydrogen on hydrogen is 0. Hydrogen on cyclohexane is treated as if it were hydrogen on methyl, which is also 0. And we're ignoring the cyclohexane interaction. So we only have these two values to account for in this Newman projection. Over here in the middle one, we have methyl next to ethyl, which has a value of 0.38. We have ethyl on hydrogen, which is worth 0.42. Hydrogen on hydrogen is 0. Hydrogen on methyl is 0. Cyclohexane to cyclohexane we ignore. And cyclohexane to methyl, we treat the cyclohexane as if it were an ethyl group, right? So we have ethyl and methyl appearing twice in this structure, technically speaking. And then on the final one, methyl on hydrogen, that's 0. Hydrogen on hydrogen, that's 0. Hydrogen on hydrogen is 0. Hydrogen on methyl is 0. Cyclohexane on cyclohexane is being ignored. And cyclohexane to methyl, that's the same thing as saying ethyl to methyl, right? Which is a total of 3.8. So by analyzing the three separate Newman projections, collectively, they're giving you the total energy that your gauge interactions are going to be in your entire conformer. So what you want to do is you want to add up all of them, 0.42 plus 0.42 plus 3.8 plus 3.8 plus 0.42 plus 3.8, as you can see right here. And added together, they give you 12.7 kilojoules per mole. All right, so once again, cyclohexane is to be treated as ethyl if it's next to a group other than hydrogen. If the cyclohexane is next to hydrogen, is to be treated as if it were methyl. That's just a quick approximation. All right, so what we now know is that this conformer is worth 12.7 kilojoules per mole just from the point of view of the gauge interactions. We're going to do the same analysis now for the other conformer of cis-1-ethyl 2-methyl cyclohexane. And starting with the carbon that bears the ethyl group, once again, we're going to look at the Newman projection going in one direction, and then we're going to look at the Newman projection going in the opposite direction. In both of them, the ethyl group is going to be on the front part of the Newman projection. So looking at the red bond, ethyl is pointing straight up, hydrogen is pointing to the left, and the cyclohexane is going to the technically the inside of the screen, that's pointing to the right. And that's what we see right here. Cyclohexane to the right, hydrogen to the left, ethyl on top. If cyclohexane is on the right side on the front part of the molecule, it will also be on the right side on the back portion of the molecule. And that's what we see right here. The cyclohexane ring is going to the back or the inside of the screen. The hydrogen over here is pointing to the left side, or technically towards you, outside of the screen. So that's what we see. Hydrogen on the left side, cyclohexane on the right, and finally a hydrogen pointing straight down. So that's what we have on the Newman projection over here. Now looking at the green bond, right, and keeping the ethyl group on the front part of the molecule, now we have ethyl on top, cyclohexane pointing to the left, and hydrogen pointing to the right. And that's what we have here on the front portion of the Newman projection. In the back portion, we have cyclohexane to the left, methyl to the right, hydrogen pointing down, and that's what we are seeing over here in the Newman projection on the back side. All right, now finally, we look at the bonds from the point of view of the carbon that bears the methyl group, right? So we have the purple bond and we have the green bond to account for. The green bond, however, is already what we did here on the second Newman projection, so that does not need to be accounted for again. But the purple bond, we haven't really looked at that interaction. So once again, keep the methyl group on the front. In that case, cyclohexane is on the left, methyl is on the right, hydrogen is on top, right? So this is the front part of the molecule, as you can see here. The back portion of the molecule, cyclohexane is going to the left and down, hydrogen is down and to the right, and then there's a hydrogen straight up, and that's exactly what we're seeing over here. And once more, cyclohexanes are on the same side of the Newman projection. All right, let's take a look at the gauge energies that we're dealing with. We have hydrogen on ethyl, which is worth 0.42. We have ethyl on ethyl, which is worth 4.6. Cyclohexane to cyclohexane is ignored. Hydrogen to cyclohexane is ignored. Hydrogen on hydrogen is basically zero, so that's ignored technically speaking. In the middle Newman projection, we have ethyl on ethyl, which is 4.6. We have ethyl on methyl, which is 3.8. Methyl on hydrogen is 0, hydrogen on hydrogen is 0, and hydrogen on cyclohexane is ignored, as well as cyclohexane to cyclohexane being ignored. And then on the last one, we have methyl on hydrogen, which is 0, methyl on hydrogen, which is 0, hydrogen on hydrogen, which is 0, and then hydrogen on cyclohexane is ignored, cyclohexane to cyclohexane is also ignored, so the last Newman projection is technically 0 from the base energy. So if we add up all these values, we get 0.42 plus 4.6 plus 4.6 plus 3.8, which is presented here. Altogether, this tells us that this structure is worth 13.4 kilojoules per mole. So now what we're seeing is that the conformer here on the right is higher in energy than the conformer on the left side. And this is the thorough way of looking at the energy differences. But the other way of looking at it, which might help you out, is that between methyl and ethyl, ethyl is a little bit bigger. So it's going to create more steric hindrance. And what that means is that if you are in the axial position with the bigger group, as it happens to be on this conformer, you're going to have the conformer with a higher energy, or the least stable conformer out of the two. Now there's one additional factor that needs to be discussed, and is the 1,3 diaxial interactions that are also steric in nature. But I want to save this for the next video. So let's stop right here, and we'll continue with the diaxial steric interactions in the next video.